Welcome to Algotech Programming Concept. In AVL Tree Part 1, I discussed AVL Tree, need of height balanced tree, that is AVL Tree, advantage of AVL Tree. As we knew in Part 1 that right skew binary search tree is unbalanced tree, and worst case time complexity of right skew binary search tree was order of n, and the worst case time complexity of this AVL tree is order of log n, so that we can perform insertion, deletion and searching operation faster here, and we can store the number of keys in less height also. And we have discussed cases of unbalanced tree structure, that what are the possibilities where the tree will be unbalanced. That was LL, RR, LR and RL combination. And constructor AVL tree on keys UV, X, Y, and we have performed various rotations to get balanced tree. Here in this video lecture I will discuss special cases of unbalanced tree structure and how to perform rotations on these cases to get balanced tree. And after that, when we learn the special cases, after that we will construct the AVL tree for these two examples. So if we perform rotation on node X, and you can see here that node X is having left subtree, that is I have denoted by alpha. So we have to perform left rotation on this node X, and X is carrying the left subtree also. And in the second case, you can see here that we have to perform rotation. We have to perform right rotation on this node Y, and Y is also carrying the right subtree, that is I have denoted by theta. So I have to perform right rotation on node Y, and Y contains right subtree, and I have to perform left rotation on node X, and X is also carrying one left subtree. So this is the special cases and how to perform the rotation so that we can get the balanced tree. So this is another example where you can see that now the first one is balanced tree, and when key 8 is inserted on first balanced tree, then this tree is unbalanced. Okay, because balance factor is computed for every node, the height of left subtree minus height of right subtree. So balance factor, you can see the range of AVL tree is 0, 1 and -1 for the balance tree. So here for node number 38, the balance factor is +2. So we have to perform right rotation, but this node number 38 is root node and also contains right subtree. Okay, so these are the special cases, and we have to learn that how to perform the rotations on these cases. So I am discussing case number 1. Suppose this is our initial tree. Okay, and I have to perform left rotation on node X. Okay, so X also contain left subtree. Okay, and one main thing to remember, that what is the in order of this original tree. Okay, so note the in order will be alpha, X, then beta, Y and theta. So after performing the rotations, we will get same in order. So you can see here, and node X contains left subtree, and the right child of X is node Y, and Y also contain left subtree here. Okay, so please note that X, we have to perform rotation on node X. X contains left subtree, and the right child of X is Y, and Y also contain left subtree, that is beta. Okay, so we know when we perform left rotation, then this node X will be placed at the left side of its right child. Okay, when this X node will be placed on the left side of Y. Okay, So obviously that the value of alpha is less than value of beta, because we have computed in order. Okay, so in order means we are in order means the values are in ascending order. Okay, so the value of alpha will be less than value of beta. So when we will put x in left side of this node y, okay, so we will put, okay, we will so when we will put x at the left side of this node y, then this beta is left child of y, then beta will be placed at the right side of x. Okay, so please watch it again, that when x will be placed in the left side of y, and if y is also containing left subtree, that is beta, then the beta value will be placed at the right side of the x. Okay, so only we will have here y and theta. Okay, so because the beta value will be less than theta, okay, and we will make y as parent node, we will make y parent or root node of x. Okay, so in this way we can perform left rotation on this tree for this node x. Okay, so what to do, that node x will be placed at the left of its right child y, and left subtree of y, that is beta will be placed at the right side of x, and we will link the pointer, we will make connection, and we will make y as a root node. Okay, so this type of structure will come after left rotation. We will learn by example that where we have to perform left rotation on node x. Okay, so this is our final result, that x will be placed at the left side of y, and this beta will be placed at the right side of x. Here you can see here. So this is the numerical example, that we have to perform rotation on node 15, the node which contain key value 15, and this also contain one left subtree. So the 20 will be our root node, and this 18 will be placed on the right side of x, means 15. So the node number 15 will contain left subtree, the value will be 11, and for node number 15 right value will be 18, and we will make this node number 20 as a parent. Okay, so if you see the in order, what was the in order here before rotation? 11, 15, 18, 20, and 22. So after left rotation we are also getting the same in order key value. Okay, this is the case 1 of a special case. Then if we have to perform right rotation on this node y, so please note the in order first: alpha, x, then beta, y, and theta. This is the in order rotation. So I have to perform right rotation on node y. If we have to perform the right rotation on node y which contains right subtree, okay, which contains right subtree, then what is right rotation? Then the node becomes right of its left child. So y will be placed at the right side of its left child x. Okay, so y will be placed at the left side of x, and what will be happen of this beta value? Okay, so obviously that beta value is less than theta, so beta will become child of y and will be placed at the left side. Okay, so beta you can see that this beta value will be placed at the right side of y, or left side of y. This beta will be placed at the left side of y, because beta value is less than theta. This is like as binary search tree. Okay, so so node y will be placed at the right side of its left child x. Okay, then right child of x will be left child of node y. The right child of x means beta will be at left child of node y, and we will join the connection. We will make x as a root node, and uh, we will make connection through pointers. This is the second case, special case, where we have to perform right rotation, and this will be our result. So we will see this by example. Okay, so we have to perform right rotation on node number 20, So 20 and this node number 22. Okay, so this node number 20 will be placed at the right side of the 15, and this 18 value node will be placed at the left side of this node 20. Okay, and we will make the connection. Okay, so simply you have to learn it so that it will be easy to solve the numerical examples. So we have performed right rotation on node number 20. So what is right rotation? The node will be placed at the right side of its left child. So please watch the AVL part 1 so that you will be expert on the rotations. What is left rotation, what is right rotation. And okay, so this is our original tree. If we perform left rotation, then the output is the second tree, and if we perform right rotation on this output, then we will again we will obtain our original tree. So it's vice versa. Okay, so here you can see by the example also that we have done in previous slides. Now this is the very special case. Okay, suppose this is node x and x is containing left subtree and y is left heavy. Y is left heavy means if you only see that this node y, z, beta, delta and theta. Okay, so you will easily perform the rotation. Okay, so if we are performing the left rotation on x, why left rotation? Because the balance factor is -2 and the balance factor is -2, then we have to perform left rotation on this particular node, that is x. So we have to see that which for which type of structure the tree is unbalanced here. Okay, so you can see that this is the right left rotation. Okay, this is the right left structure. Due to right left structure, this tree is unbalanced. Okay, so we have to perform here right left rotation to get the to get tree balance. Okay, hence double rotation will be required. So this tree is unbalanced due to right left structure. Here you can see. Okay, so we have to perform right rotation and then left rotation. Okay, so we have to perform right rotation on the mid node. Okay, then we will perform left rotation on node number x, which contains -2 value. So for negative value we have to perform left rotation. So this is right left combination, so we have to perform right rotation on node x. So you can see that when we will perform right rotation on node x, then please see the structure here in the previous in this slide. So you will easily we will place this y node in the, because we have to perform right rotation, so we have to place this y node towards the, we will place this y node at the right side of this node z. When we will place this y node at the right side of this node z, then delta will be placed at the left side of y. Okay, so here you can see that this y node is placed on the right side of the z. This y node is placed in the right side of the z, and this delta value will be placed on the left side of y. So in the first right rotation, that was second case, so you can watch again. Okay, and this is our node x, and then for node x we will perform left rotation. So what is left rotation? So in the left rotation, the node will be placed at the left side of its right child. So right child of x is z, and x will be placed at the left side of z. So when we will place x, then obviously that alpha value will be less than beta. So alpha is less than beta, so alpha will be placed at the left side, and this beta will be placed at the right side of node x. So you can see that this is node z, and x is placed on the left side, and this beta value is placed on the right side of x. So please watch again to learn the case rotations on special cases for case number 1 and case number 2, and remember that in order. You can see the in order of this tree. In order of this tree is alpha, x, beta, z, delta, y and theta. So after performing the right left rotation, we will achieved same in ordering of keys. Okay, and we can say that our tree is here balanced tree. So now we will do exercise. So these are the keys. If we make the binary search tree of these keys, then our tree will be like this. Okay. So the height, you can see that after insertion of node 8, we are getting height 4. Okay. So this is a type of binary search tree. Okay. 38 is less than 41, so place in left side. Okay. So these are the step by step insertion you can see here, and we are getting height 4, and we can perform we can store these keys with the help of AVL tree or height balance tree in less height. Okay, either we may get height is equal to 2 if we store these keys with the help of AVL tree. So we are starting. So this is the root 41. 41 is root node, and we have computed balance factor here, right, height of left subtree minus height of right subtree. So this is 0. Then we have inserted 38, that will be placed in the left side. Then we have placed 31, that will be also placed in the left side of row number 38. Here balance factor we have computed, and the height of left subtree minus height of right subtree. So here for node number 41 we have obtained the balance factor is positive 2. Positive 2 means we have to perform right rotation on this node number 41. So what is right rotation? The node will become right child of its left child. So the left child of 41 is 38. So 41 will become the right child of its left child, means 41 is placed in the right side of this node number 38. Now 38 is root node here. We have again computed balance factor. You can see that tree is balance here. Then after that we will place we will place 12. Okay, so 12 will be placed, and because this is binary search tree, so 12 will the 12 will be compared with the root node 38 is less than, then it will also come in left side, then compared to 31, then it will place on the left side. Here we have computed balance factor. So balance factor is ranges 0 to 1, 0 and 1. So this tree is balance here. Now we have inserted node number 19. So node number 19 will be compared with the root node, then it will be placed at the right side of this node 12. So here we have computed the balance factor here. Balance factor is 2 for node 31, and this tree is unbalanced due to left right rotation here. Okay, so because we have computed balance factor, and we have to resolve it for the node number 31. Okay, so this is our left right rotation, so we have to solve it, means we have to balance it, and we will, what will be the result of this balance tree, we will put on the left side of this node 38. So we are performing the rotation, left right rotation. So left rotation, first we have to perform left rotation on mid node. So this 12 node number 12 will be placed at the left side of this 19, and we have to join the pointers here. So 31 will be root, and this value is positive, so we have to perform right rotation on this node 31. So the 31 will be placed at the right side of 19. So 19 will be a root. So this value will be placed at the left side of node 38. Okay, so this value is placed on the left side of 38. Now this tree is balanced, and we have to insert node number 8. So node number 8 will be placed in the left side of this node number 12. So here we have computed the balance factor for every node. So we can see here that the balance factor for node 38 is positive 2. So this tree is unbalanced, and we have to perform right rotation, and we have to see here that this node 38 is root node, and it is also containing the right subtree. Okay, so this is the special case. So this 38 containing 41 will be placed at the right side of 19, where this node 31 will be placed at the left side of this node 38. Okay, so this is the special case. So you can see here that what is happening here, that if y along with theta will be placed at the right side of this x, and beta will be placed at the left side of y. Okay, so beta is placed at left side of y, and we will merge the operation. Okay, so x will be the root key here. So here you can see that 38 right side, left right subtree is 41. This 31 will be placed at the left side of 38. Okay, then here we will get 19, 12 and 8, and we will join. So 19 will be our 19 will be our root node here. So this is our balance tree. So like this we have obtained the balance tree structure here. So the height of this tree is 2. So the same number of keys, 6 number of keys in right skew. If we are storing these 6 keys with the help of binary search tree, then height was 4, and here in AVL tree the height is 2. So the searching operation, insertion, deletion operation is faster in AVL tree, and we will perform the searching, insertion, deletion in order of log n base 2 in the worst case and average case. And for searching we will obtain the constant fact time if our searching is placed in the first case. Okay, so in the next lecture we will also solve this numerical example for 6 keys where we have to perform some special rotations here. Thanks for watching. In the next lecture we will solve this numerical example. Thanks for watching.